Thank you so much for the invitation. So I'm also going to be talking about data, but a different kind. So we've been hearing from Carlo and others about some of the pitfalls of the official data that people are looking at when thinking about measurement of food crisis. That's not what we're doing here. We're actually taking this data at face value and trying to see whether we can predict them in advance, which we know is very useful because the more we can anticipate food crisis, the better we can act. So I'm going to be talking about a research paper of mine that just came out a few weeks ago in Science Advances that was done in collaboration with colleagues at Google and New York University. It's called Predicting Food Crisis Using Natural Language Processing of News Streams. I also wrote a blog post about this to make it accessible to a wider audience, so I encourage all of you who prefer to stay away from formulas to look at the blog post instead. And we've been fortunate to have been covered by more than 15 news outlets worldwide. So today I'm going to try to convince you that this approach could be transformative for quantifying food insecurity. So first of all, why does it matter? I don't think I'm going to convince any of you that there is a strong motivation to better predict food crisis. And obviously the reason is especially important these days because food insecurity has sharply deteriorated in recent years due to intervening shocks, including COVID-19, also climate change and conflict. And it's obviously now a top priority of the international community. And there's actually considerable evidence showing that promptly responding to emerging risks of food insecurity saves lives, preserves the livelihood of the most vulnerable, and lower humanitarian costs. And so that creates a need to develop better early warning systems for food insecurity. The problem is that these systems often rely on data that is either incomplete, delayed, or outdated. And so we were wondering, can we do better? Can we, for instance, look at non-traditional data sources and machine learning to improve the prediction of food? So our idea was quite simple, actually. We were thinking that text data, and especially text data that we could collect from news articles, could help better anticipate food crisis. And the reason why we were thinking that this could work is that the risk factors that generate food crisis, such as conflict, floods, pests, drought, etc., are often mentioned in news articles on the ground before being reflected in traditional risk measurements, such as food price indices, NDVI indices, and the like. So we wanted to find a way to track the signatures of risk factors appearing in news articles all over the world, construct indicators based on this information, and then show whether these new types of indicators could help predict indicators of food crisis. And news data, again, I think are a great data source to do this kind of thing, because we could access, especially through news aggregators, daily articles since the 1980s. So we had access to a very long time series of data at high frequency, and data that is also geographically indexed from all the regions in the world. So how did we go about predicting food crisis using news data? I'll just briefly explain the method, not going into too much detail, but I'm happy to answer more if you're interested. So we started by collecting 11 million news articles, a very large data set that focused on 37 food insecure countries since the 1980s, and that were published by more than 5,000 news sources. So pretty large data set. Then from this, we developed machine learning techniques, deep learning more specifically, to identify signatures from the text. So it's really specific keywords and phrases that were relevant for food security. So you cannot see very well in the slides. Maybe you can see it on the iPad in front of you. I actually zoomed in on some specific signatures from the text that the model was able to pick up. And for instance, the zoom is looking specifically at climate-related shocks. And we see that it can pick up very specific terms such as abnormally low rainfall, shortage of rain, prolonged dry spell, etc. So very specific. effects that are characteristics of future outbreaks. Then what we've done is we actually built indicators by tracking these signatures across districts and time. I'm showing you one example here for conflict, but we have, as I said, about 170 of these indicators. And then we plugged them into a machine learning model to predict the IPC phase of food security. So many of you probably know what the IPC phase is, the ground truth indicator of food security that we collected from FuseNet. It's published every 4 months at the district level, and it quantifies food security on a scale from 1 to 5. So 1 when food insecurity is minimal, to 5 when there is a famine. So that's basically what we're trying to predict. Before telling you what we found, let me show you how this kind of predictions are currently being done. So we actually compare our work to 2 existing baselines. The first is the expert forecast that FuseNet publish. Every time they publish a number about the food security situation on the ground, they also publish a forecast of what experts think the food security situation will be 4 months in the future. That's the first thing we compare ourselves to. And the second is a predictive model. It's a random forest regression, but a predictive model that takes as inputs traditional data and aims to predict what the IPC phase, so what's the ground truth likely to be 4 months in the future. And it takes, as I said, traditional data, including conflict fatality count at district level, food price indices, rainfall, evapotranspiration, and NDVI. So what do we bring to the table? Well, we take the same prediction model, and instead of using traditional data, we replace them with our data, the news indicators that I was describing before. That's what I call the news model. That's the first thing we bring to the table. The second is, instead of replacing the traditional data with ours, we combine them. That's what I call the news plus traditional model. Okay, so that's the 2 things we do. And what do we find? So there are 2 questions we try to ask. The first is, what is food security likely to be in a district 4 months from now? That's the results I'm showing you on the left. Now remember, in this case, food security is measured on a scale from 1 to 5. So if you listen to what the expert forecasts tell you, well, the forecast error that the experts make is about 0.19. So on a scale from 1 to 5, the average sort of expected error is 0.19 from the expert forecast. The traditional model does substantially improve that. The error is about 0.15. Now, if you look at our model that uses news instead of traditional data, the expected error is 0.10. And then if you combine news and traditional data, you get an error of 0.08, which is a 45% improvement compared to the best, one of the best models we could find out there. So that's already a pretty significant result. Then the second question we answer is, 4 months from now, will there be a food crisis in a district? And here, again, we do the same kind of comparisons. So if we look at the data we're trying to predict, we're doing these predictions over the period 2010 to 2020. Unfortunately, I don't yet have more recent data in this work, but we're anticipating to update that very soon. So over this period, we had about 1,800 food crisis events in the data. So here what I define by a food crisis event is when the IPC phase goes to, rises to a level of 3 or above for at least 8 months. And so we're trying to predict whether that's going to happen 4 months in the future. If you look at the performance of experts at this prediction, they are able to predict these outcomes about 51 or 52% of the time. The traditional model is able to correctly predict these events 60% of the time. Now, if you look at what we can do with the news indicators only, we can predict this food crisis 77% of. And finally, if you combine our data, the news indicators, and traditional data, we can predict this food crisis 91% of the time. So the takeaway here is really that this method of predicting food crisis using news indicators can drastically improve the prediction of food insecurity relative to both experts and the current type of predictive models that are being used. And that what we see is that it's not just a substitution, but it's really combining this new approach with existing data that gives the best performance. I'm not showing it here, but we're actually seeing consistent improvements in the predictions across all the 37 countries that we looked at. These results here in this slide are for 21 countries, for which we have traditional data for comparison. But in our paper, we're showing that this works for all the 37 countries for which we have FuseNet data and expert forecast for this. And finally, this is a prediction 4 months in the future, but we find that our news indicators actually carry predictive power up to 12 months in the future, which is obviously very useful to use this kind of model to have sufficiently time for action. Now you may think, okay, so that sounds interesting, but I don't understand machine learning. I don't understand really what these numbers mean, and maybe you don't have experience with kind of models. Maybe your experience with machine learning is limited to playing with ChatGPT and realizing that it's prone to hallucination, and that you're really concerned about this approach just because it's very black box, which I think is totally understandable. And so in the few minutes that we have left, I'm going to try to convince you that actually it's not black box. It's actually quite transparent and could be very impactful for decision making. And for this, I'm going to take one example from Ethiopia, specifically from the Mahjong region in Ethiopia. So in Ethiopia, there was a severe drought in 2009. And when we looked at the data, especially the data from the Mahjong region, we saw that there was a food crisis that was declared in that region, but that crisis was only declared in July of 2010. So if you look at the blue plot at the bottom, it shows the IPC phase that goes from a normal level 1 to a crisis level 3 in July in 2010. Now, if you wanted to anticipate this event using the traditional data that people typically use, well, you could, for instance, look at the rainfall index, try to predict that crisis, and that's the black line I'm showing at the top, and it's basically close to its median value. So you don't really see much action, at least looking at rainfall going into the crisis. And that's the same story if you look at other types of traditional data that people typically use for this kind of prediction. And so as a result, prediction model that's trying to predict that crisis 4 months in advance would fail to predict it. That's what I'm showing in the turquoise line at the bottom. It's not able to predict it in advance. What do we see from the news, on the contrary? Well, that's the green indicators I'm showing you at the top. These green indicators are the frequency of mentions of climate-related shocks in the news, so expressions like drought, failed rain, abnormally low rainfall, prolonged dry spell, etc. Kind of signatures from the news that I was showing you earlier. And so what we see is that they peaked 6 months before the crisis, and they stayed at the high level going into the crisis. As a result, if you use this information into our predictive model, we're actually able to predict the crisis 4 months in advance. That's the pink line I'm showing you at the bottom. That's 4 months ahead prediction, and it's correctly showing the jump from 1 to 3. But what's even more interesting is if we ask the model, why are you making this prediction? And the way we do this is that we basically eliminate what we feed into the model, and we see when the prediction, when the model is not predicting a crisis anymore. And we see that when we remove the information coming from these climate-related terms, climate signatures, it's not predicting the crisis anymore. So that's really showing us that we can pinpoint why the model is making the prediction that it's making. And we have a couple more of these examples. So to conclude, I would like you to take away that this new method can drastically improve the prediction of food crisis outbreak up to 12 months ahead. And it could give a crucial time advantage to better anticipate and respond to future outbreaks. Even a few additional months to implement a cash transfer or food distribution program will have a large impact on the outcome. And more importantly, the model prediction can be interpreted and explained to the decision. Of course, we're very excited about this, but we know it's far from being perfect. It's a technical approach, and it doesn't resolve all of the issues that come with it. And we even think that from a technical standpoint, there are many different directions for improvement. We want to expand this by incorporating information from local languages beyond English, by including additional countries beyond the 37 that we're studying. And we are currently in the process of fundraising to produce an automated data system to make this kind of information, the indicators and the predictions that we're making available as a public good. And through a system that could set red flags to both NGOs and disaster risk management institutions. I'm happy to talk more about this